The upcoming talk will bring back memories. At least they brought back memories to me when any of these sounds produced by platforms like Super Mario World, Chrono Trigger, Super Metroid, and some more are being played. Our speaker will explain and share with us how that actually works, how that sound synthesis works, and give us a deeper understanding how these most favorite memories of most of our youth were actually being created. So please give a big round of applause for Kleines Filmröllchen.
Hello and welcome everyone. What you just heard was the intro to Super Metroid, and part of the amazing atmosphere that this intro has is of course the sound. This is the ultimate SPC700 talk, the talk about the architecture behind the sound of the Super Nintendo Entertainment System. This talk is part of a series of ultimate talks where we try to convey as much as possible about a certain architecture or computer in 1 hour. So how did I steal a microphone? Well, actually, they gave it to me. I'm barely known for all of these things. The most important one for this is that I am the author of the SPC700 assembler for this architecture. That's what got me interested. So first of all, let's set the scene. Super Nintendo Entertainment System came out in 1990, and this is roughly how it is laid out internally. So the main CPU has access to the cartridge RAM and ROM, and it runs all of the game logic and all of the graphics. And the PPU, the picture processing unit, is actually just a very dumb graphics processor. It needs to be told very precisely what to do. So the CPU has to spend a lot of time telling the PPU exactly what tiles to draw and what sprites to draw and so on. On the audio side, that's actually completely different because the S-SMP is a full general purpose microprocessor which talks to the synthesizer chip, the S-DSP. It has its own memory space with RAM, and it doesn't have access to any of the cartridge memory. So for some reason they decided that an audio coprocessor was necessary, and that makes this architecture very interesting. You can even see that in the boards. Here on the right side you can see the two PPU chips and the CPU chip. On the left side, the very top chip is the S-SMP, and below that the DSP chip. And even later on, when they combined multiple chips into one in later board revisions, they still kept the CPU and PPU chip on the lower left, the large chip, and the SAPU chip with DSP and SMP on the upper right. This is a die shot of that. It also contains the memory. You can see the S-SMP chip on the upper left and the memory audio RAM right of that, and the lower section is the DSP chip. So this audio processor was very much ahead of its time. In a time where most consumer console audio hardware was doing frequency modulation synthesis, FM, they had full 15-bit 32 kilohertz samples, 8 voices could play those. They had modern ADSR envelopes, pitch modulation between voices, allowing you to do FM regardless, echo and FIR filters, and also a simple noise generator. So this talk will roughly be split up into 3 parts. First, I'm going to talk about the CPU architecture, then I'm going to talk about the hardware sample format called BRR, and finally I'm going to talk about the DSP hardware itself. So the architecture is often compared with the 6502, and while it was clearly explicitly based on the 6502 by the Sony engineers who designed it, it came out very differently. So first of all 256 opcodes are occupied. This is a full opcode map. And that's already very different from the 6502, which has a very small part of its opcode space actually occupied. It supports binary coded decimal arithmetic, has a lot of support for single-bit computations and 16-bit instructions, also hardware multiplication and division, and some very unusual branch and call instructions. In practice, it runs at the same speed as the 6502, even though it runs at twice the clock rate. All the instructions take roughly twice the amount of clock cycles, so it's practically the same speed. It's an 8-bit processor. It has a 16-bit memory space, so 64 kilobytes, and it has interrupt support, memory mapped I/O, timers, and communication ports for the main CPU. These are the registers. The accumulator is where all primary computations go through. The index registers X and Y are mainly used for special addressing modes. The program counter points to the current instruction, 16 bits. And the stack pointer actually only has 8 bits because it always lives in the one page of memory, so the upper 8 bits are fixed to hex 01. And the program status word is the flag register. It contains normal processor flags like the negative flag, the overflow flag V, the half carry flag, the 0 flag, and the carry flag. It also contains the P flag and the 2 interrupt flags. So this is what the memory map looks like. Memory is split up into pages. Every page is 256 bytes large, so a page can be identified by the upper 8 bits. That's how we get the 0 page with hardware registers, and then the 1 page, which also contains the stack. And there are some addressing modes which access the so-called direct page, which is either the 0 page or the 1 page. And which page it is determined by the P flag here in the flags register. This is very similar to the 0 page behavior of the 6502, and that's why I'm going to say direct page in general, because it can either mean the 0 page or the 1 page depending on processor state. All of the memory is occupied by audio RAM, except for some of the I/O and RAM regions. And bit instruction addressing can only go up to a very small part of audio RAM. And finally, at the very top of audio RAM, or at the very top of the memory space, we have the 64 bytes of boot ROM, which can also be switched out for more audio RAM. That's where the chip boots initially when you start it up. So let's talk about addressing. This is a very simple instruction, add with carry A with direct page 5.1, which means that from the direct page address memory location 5.1, we will load memory, and now this depends on whether you have the direct page bit set to 1 or 0. It could be either 0151 or 0051. In terms of the address, but I'm going to assume here that it's the 0 page, so we load the value 77 and add that to the accumulator. More interesting is once we introduce memory indexing. So this is 50 indexed with X, so we take the immediate address and add it to the X register, giving us the address 52, and now we load from direct page address 52 and add that to the accumulator. We can also use X directly as an address, so as a pointer effectively. So in this case, loading from memory address 02. This is also possible with the Y register, and also you can directly increment the X register after the operation, allowing you to step through memory more efficiently. And all of this allows you to use X and Y as array indices effectively, which is very useful. You can also do direct addressing on the whole memory space, specifying a 16-bit memory address. However, that means that the instruction will be 3 bytes instead of 2 bytes, 1 byte for the opcode and 2 bytes for the memory address. And also it will be slower, so you should always prefer using direct page addressing when possible. What is not possible on the whole memory space is indirect addressing. So now we do indirect 07 plus X. So we take the immediate 07, add it to the X register, and now what we load from address 08 is not the actual value that we want to add. Instead, it's a 16-bit pointer. And because the SPC700 is a little endian architecture, we now load the pointer 7F00, a full 16-bit pointer, and now load from that address and add it to the accumulator. This is also possible with the Y register. Instead, here we immediately load the pointer at the direct page memory address and then add Y to the pointer, allowing us to step through the 16-bit address instead of just the direct page, which is arguably more useful. So let's talk about some actual instructions. The Many instructions share the move mnemonic. These are all of the load instructions which load some place in memory into one of the 3 general purpose registers. The only addressing mode we haven't seen here is the ones prefixed with a hash. Those just load an immediate instead of loading from memory. So for example, move X hash $20 will load hex 20 into the X register. The store instructions are the exact opposite. They also use the move mnemonic. They store one of the 3 registers into memory. Register transfers also use the move mnemonic, and this is one of the only ways of accessing the stack pointer directly by transferring it to and from the X register. You can also load memory directly. You can load one direct page address directly with a value of another direct page memory location, and you can load immediates directly into the direct page. Arithmetic instructions can use fewer addressing modes, all of these that you can see here. There is add with carry, subtract with carry, compare and set flags, which effectively only performs a subtraction but doesn't store the result anywhere. It just sets the processor flags, bitwise and bitwise exclusive OR. And there's also some single argument instructions, increment, decrement, left shift, rotate right. The shifts and rotations only perform one operation in their respective direction. Now, I told you that there would be binary coded decimal support, and binary coded decimal is a way of storing decimal numbers in hexadecimal or binary numbers in a way that it can be displayed to a screen more easily. However, this is an audio coprocessor, not a video coprocessor. So like the binary coded decimal support is entirely pointless, and I'm not going to explain how it works. The only useful part really is the exchange nibbles instruction, which will exchange the 2 4-bit nibbles of the accumulator. So there is some support for 16-bit arithmetic, always with the W for wide, I guess, or for word. And it usually uses the combined YA register, which simply combines the Y register and the A register into one 16-bit register. Now, I promised a hardware divider, and here it is. The multiply instruction will multiply the Y register with the A register and store the combined 16-bit result into the combined YA register, so not losing any sort of precision. And the divide instruction will divide the combined 16-bit YA register by the X register and store the result into A and the remainder into Y. And this is by far the most expensive CPU instruction. It takes 12 cycles, but it's still vastly more efficient than anything you can write in software. And this is actually quite a useful feature because in audio you have to do a bit of multiplications and divisions sometimes. So I imagine that's quite useful. For manipulating the stack, there's traditional push and pop instructions, and you can directly push and pop the flags register as well. Now, for bit computation, there is a whole host of support. You can set and clear a specific bit in the direct page, and the notation here is that the dot and then the number afterwards signifies the bit within the memory address. There's also test and set and test and clear instructions, which perform the exact operation as you would think given their atomic primitive names, except it doesn't really make sense for atomic operations since you only have one processor. There is various logical and move instructions, and they use the carry flag as a single bit accumulator effectively. And also you can invert the bit coming from memory before performing the operation that's signified with a slash in the assembler notation here. So there's quite a few possibilities. And because the carry flag is used so much for single bit computations, there's also a whole host of manipulation instructions just for that. Let's move on to control flow. Normal branch instructions take an 8-bit signed offset, so they can jump up to 127 bytes forward and negative 128 bytes backwards from the next instruction after the branch. And you can either branch unconditionally or conditionally on most of the processor flags. You can also branch depending on whether a bit in the direct page is set or cleared. And there are some weird branching instructions. The compare and branch if not equal instruction will compare the value in the direct page to the accumulator and only branch if they are not equal, which saves you a compare. The decrement and branch is not zero instruction will decrement its argument and then branch to the offset if that wasn't zero, which allows you to write loops very efficiently. So you can put this instruction at the end of a loop and jump back up to the loop. And if you initially set up the loop counter, that gives you a very efficient way of writing loops. For jumping to further away places, you can use the jump instruction, which jumps to a full 16-bit address. There's also an indirect jump instruction, which allows you to use jump vector tables in memory. For calls, there is the normal call instruction, which will store the program counter to the stack and restore it on return. There's also the pcall instruction, which can only call into the uppermost page of memory, and you can put some very important commonly used routines up there, I guess. It's faster and smaller in terms of encoding. And then there's also the 16 tcall instructions, which take up quite a large part of the opcode encoding space, but they effectively call into a hardware-defined subroutine table, starting at FFC0 and going up there in like 2-byte increments. So if you have, you can store like function pointers there, which allows you to call even more important, even more frequently used functions and their locations up there. And you can return from all of those with the return instruction because they all push the program counter in the same way. There's some instructions for manipulating the other flags. Importantly, of course, you can clear and set the p-bit, which allows you to control which page is the direct page. You can, there's a NOP instruction and a halt instruction. Now, I told you that there would be interrupt support. Well, external interrupts are not connected on the hardware. Software interrupts are pretty much useless unless you maybe have a debugger, but I don't know. So interrupt support is mostly useless and pretty much unused on the SPC700, so I'm not going to explain any of the interrupt support. More interesting are the hardware registers, 16 of those starting from address 00F0 to 00FF. First two are internal CPU control registers. The next two control the address of the DSP that you want to write to and the data that you want to read to or write to or read from the DSP. So this is how you access the hardware registers of the synthesizer, and we are later going to see quite a few of those registers and where they live. There is 4 communication ports for talking to the CPU. There is 2 auxiliary ports which connect to 16 wires on the external chip. However, they are also not connected, so they're also pointless. And then there's timer control. So the test register pretty much shouldn't be touched because it's only intended for internal testing purposes. There's 2 ways to enable or disable timers. You can disable all writes to RAM. You can crash the CPU by writing to bit 2 if you ever wanted to do that. And also you can add extra wait states to ROM and I/O accesses. Because audio RAM is shared by both the synthesizer and the SPC700, they have to wait for each other, and the synthesizer always takes priority. So there's a very specific cycle of wait states, and you can add extra wait states on top of that if you really want to, which is just going to slow your program down, so don't do it, I guess. More useful is the control register, which allows you to enable or disable all the timers, which allows you to clear the ports in groups of 2, and also allows you to set whether the top of audio RAM contains the boot ROM or extra audio RAM, because you usually don't need the boot ROM after you've booted. So the timers, they run at different frequencies. There's 3 of them. T0 and T1 run at 8 kilohertz. T2 runs at 64 kilohertz. And their respective division register controls what frequency it's divided down to. And a division value of 0 actually means divide by 256, which allows you to go down to 31.25 hertz. And the timers don't cause any interrupts. They instead count up as 4-bit counters, and you can read the value out from TN out. That's the only way to access their value. So now let's switch perspective a bit. As I talked about earlier, this architecture, the SPC700 has no way of accessing cartridge memory, so you need to upload cartridge memory into audio RAM somehow, like for all of the samples, all of the code, all of the other data that you need. And that's why the boot ROM exists. It implements a very simple, I don't have time to go through it, but it implements a very simple upload routine. This is a commented disassembly that you can also find on the internet. So the way that this works from the CPU's perspective is, for starting the first transfer, we write the target address of the memory that we want to upload into ports 2 and 3. We write a non-zero value into port 1, and we write 0 into port, we write the magic value CC into port 0. So what is important to remember here is that those ports are full duplex. So when I, from the perspective of the CPU, write something into port 0 and read back that port 0, again, I'm not going to read back what I just wrote. I'm going to read back what the S-SMP last wrote into it. So it's like full duplex, and I can't read back what I wrote. So it does make sense to wait for the S-SMP to respond with the exact same value in the exact same port, because they are full duplex. So now for sending more data, I can send the data into port 1 and increment the data index into port 0 and wait for the acknowledgement, which is sending the exact same index back into the port 0. And the data index can increment and overflow past 256, so we can send arbitrarily large blocks. The S-SMP doesn't care. But if you want to start a new block in another memory location, you have to set up a new target address, a non-zero value in port 1, and then anything except the last index plus 1, which tells the S-SMP to stop the current transfer and start a new one. And for ending all the transfers, you write another address into ports 2 and 3. You now write a 0 value into port 1 and anything except the last index plus 1 in port 0. And now this address is interpreted as a jump address where the S-SMP will jump execution to. So from that point on, you can take control over the system and do whatever you want. Okay, that's basically all I have to say about the architecture. Let's move on to the audio side of things, to the BRR sample format. So, first of all, importantly, there's a difference between what you would call sample in music, which is a small snippet of audio that you're playing, for example, a single note of an instrument, and what we call a sample in digital signal processing, which is a single digital value of a digital signal. So unfortunately, I have to use both terms interchangeably. I hope it's not too confusing. Anyways, first of all, I should maybe give you a little bit of a crash course on how digital audio actually works. I even have a YouTube video for that. I should link that maybe. Audio, initially, analog audio is just very fast movement in air. So it's like the sine wave you saw initially. We can record that with a microphone, and then we have an analog representation of that in electricity, voltage over time. And for making that digital, we first have to sample it with a sample rate, like we saw here. So at regular intervals, we take note of the current voltage, and how often we have to do that depends on a bunch of complicated math, but effectively we have to do it more than 40,000 times per second, so a sample rate above 40 kilohertz. And now we have those analog voltages, which we then need to quantize into concrete integer numbers, like is happening here, in this case 16-bit numbers. And then we can just store those and reproduce the original sound perfectly by doing the entire process in reverse later on. And this way of storing things is called pulse code modulation. And if you just store those samples into a file, you basically have the WAV file format. So learn something else important and useful here, except for old, outdated architectures. So what is this bitrate reduced thing? Well, the amount of data that comes out of a raw PCM stream is way too much to actually directly use in the SPC700 with its 64 kilobytes of memory, because that would mean you could only store about 2 seconds of audio, which is absolutely nothing. So what you have to do is reduce the bit rate, and that's where this name comes from, but it's kind of a misnomer. More correctly, we should call it adaptive differential pulse code modulation, ADPCM. Adaptive means that the compression that we apply adapts to the input. Differential means that we mainly store the difference between samples, and PCM is what I just explained to you. So the bits that come out are 15 bits. That's the bit depth. There is some places where we use 16 bits. There's various complicated rounding modes and switching between those two bit depths. But effectively, the sample are 15 bits. And the playback rate is 32 kilohertz of the entire synthesizer system, which is exactly one sample per 32 CPU cycles. The synthesizer and S-SMP run in lockstep effectively. They share clock rates everywhere. So BRR is split up into blocks. Each block has 9 bytes. 1 byte is a header, and 8 bytes contain 2 4-bit samples each, signed samples. So that's 16 samples, which can have a range of -8 to +7. And the header initially contains the loop and end flags, which determine whether the sample ends after this block, and also maybe whether we want to loop back to an earlier point in the sample so that we can play part of a sample repeatedly. So the incoming nibbles are initially shifted, given the shift value in the header. The shift is offset by 1, so actually to have no shift at all, it means you have to use a shift value of 1, and a shift of 0 shifts 1 to the right, which is pretty much pointless. Shifts above 11 or the value of 12 don't make sense, because remember we have 4 bits here and we can only go up to 15 bits, so we can only usefully shift by 11. So that's why shift values of 13 to 15 are a hardware glitch. It's consistent, but it's technically a glitch. And don't use it. And this entire shift process, of course, increases the range of our incoming values from -8 to +7 to like much larger range. But importantly, now we pass it through a filter. The filter is also specified in the header, and there is 4 of them. And the filter 0 just uses the values that we just got from shifting as is, verbatim, as we would say. And this is useful if you don't know what the previous samples are. For example, at the start of a BRR audio sample or at the start of a loop point. The first filter effectively adds the previous output sample to this current input value that we are getting in. And this means that this value that we're getting in is just encoding the difference between the previous sample and the next sample. And that's where the differential or delta coding comes in. And because samples in waves are always pretty close to each other, this is actually already very efficient. The filter 2 does something similar, except it uses +2 of the previous sample and -1 of the sample before that, which, if it was actually +2 and -1, it would be exactly a polynomial order 2 predictor, which means that, again, I don't have details to go into all of the math behind how this works and why it works, but effectively we can use parabola, so polynomials order 2, to approximate how the samples behave locally, because that actually matches up because of Taylor series, and then that allows us to predict where the next sample is, and this gives us even better compression sometimes than filter 1. Now, filter 3 is weird because it's similar to filter 2, except the values are kind of off, and I have no idea what they were trying to do with that. I guess it exists, and you can try compressing with it, but I have no explanation. So this entire process of taking previous samples, multiplying them by certain factors, and then adding the next input value into it is called linear predictive coding, and it's still the state-of-the-art compression method for modern lossless compression algorithms like the free lossless audio codec and ALAC. So you've already understand 50% of how those audio formats work. You're welcome. We still have kind of a storage size problem, because if we want to play like musical instruments, we would need one separate sample for every single pitch, and that would already mean that we would need like 12 different samples for just one octave, and that would of course again blow up our memory requirements for samples. So what the hardware can do instead is take a single sample and play it at different pitches, so that we only need a few samples for an entire whole instrument. So the way that this works is that there is a per-channel pitch counter, which is incremented by the 16-bit pitch hardware register. So the N here indicates the voice. Of course, there's one register per voice. And that's done for every single sample that the DSP outputs. The pitch counter is not really 16-bit, it's 4.12-bit fixed point. So the upper 4-bit indicate the index within the current BRR block, of course, 16 samples. And the lower 12-bit, or at least the upper 8-bit of that, are used for interpolating between BRR samples. I have some examples for like the pitch values, the fixed point pitch values you can put in, and what playback rate that would roughly equate to. It is clamped at around 4 times playback rate, so 2 octaves. This is maybe a better visualization of how that works. If we're playing at half speed, that effectively means that we increment the orange line, which is our current position, our current pitch value, the internal register. We increment that by half a sample every time, so we play each sample twice. The 3000, for example, would mean that we only play every third sample and we skip 2 samples in the middle. But of course, we don't just do that. We don't just repeat samples and skip samples, because that would sound absolutely horrible and nobody would want to listen to that. So what we do instead is we interpolate between samples. And for various technical reasons, we only have access to the next 2 and the previous 2 sample. And now we have this playback position, again in the orange vertical line, and we want to figure out how to sum up those samples, interpolate between them, to get a rough approximation of what the sample would sound like if we inserted more samples in between. So we don't just linearly interpolate, that would also sound kind of horrible. It turns out that using a Gaussian curve or a bell curve is actually a very good idea. Signal processing people will know why, but it's not important for our purposes. And the way that this interpolation is done is that we have a hardware register, a hardware lookup table. I have written it in big N, which contains all of the bell curve factors, and it only contains half of a bell curve because it's exactly mirrors. There is 512 entries and goes up to hex 519. So if you stare at this long enough, you can convince yourselves that these indices actually make sense. The I is the offset within the current sample. It's the orange thing in the internal register here, the 8-bit interpolation table index. And then we have to scale the entire thing down at the end. But that's how we can very nicely interpolate between samples, and it actually sounds pretty good. Now, the only thing that you have to be careful with is that this will cause a low-pass filter to be applied to the sample, even if it is played at the original 32 kilohertz playback rate, so one input sample per output sample. So if you want to avoid that, you have to apply a pre-emphasis filter, so you have to use the inverse filter of this, which is easy because it's linear and invertible. And many tools do that. SPC700 does that, BRR tools does it, but there are some games where you can tell that that wasn't actually properly done. So yeah, something to look out for. We have now explained everything about how the sampler format works, and all of this decoding happens in hardware, of course, and I'm going to talk more about how the hardware works. This is a full, or pretty much full, slightly simplified block diagram of the DSP's internal pipeline. The orange parts exist, one for each voice, and the gray parts are registers or memory where, the DSP interacts with those. So first of all, the part that we've mostly already seen, BRR data comes from main memory, is indexed by the source number and the directory, and then goes into the BRR decoder. And the BRR decoder writes out the corresponding AND-X flag for each voice when it sees a loop or an AND flag in its block, and stops playing or loops back depending on what the exact flag was. So AND-X is one of those many registers that contains 1 bit for each voice and just signals something for each voice. And you can see there's various registers where the DSP writes values into for software to read back and be informed about what the synthesizer is doing, and the inverse is obviously also true. So the BRR decoder passes its samples into the pitch calculation thing with the Gaussian interpolation that we saw. And now importantly, wrong direction. Importantly, it doesn't just use the pitch register, it actually does pitch modulation. I lied to you earlier. So we use the upper 11 bits from the output of the previous voice. That's the slightly darker orange thing that goes down below everything else. That comes from the previous voice, and we use that, multiplying it with the pitch register if pitch modulation is enabled for this voice. And the way that the multiplier works is that it can, if it has maximum output volume, it's going to multiply the pitch by 2. And if it's at a minimum output volume, it's going to multiply by 0, and in the middle is 1. So it's a bit non-linear, but you can do some interesting modulation things there, I think, because most games don't use it, but you could in theory. The output of the pitch calculation is the actual BRR sample subsystem output, and we can now switch between that and the noise generator, which is global for all of the voices via the noise on flag. And then we combine that output signal with the envelope generator's envelope volume. The envelope generator takes in the gain in IDSR registers and also the reset signal, and outputs an 11-bit envelope factor, which is also written to a software-readable register. And the output of that multiplication is basically already the output sample of this voice. We get that out into the VN out register for software to read back, at least the upper 8 bits. And then we split the path into stereo. So here we get the left and right channel volume for this voice. And I'm only going to show the left voice, left channel now, because the right channel is exactly the same. So on the master path, we add up all of the different voices, and we multiply by the master volume corresponding to the channel. On the echo path, we can first of all enable or disable echo for each voice individually. Then we add up all of the voices that do have echo enabled, and then we enter, wrong direction again, then we enter the echo buffer subsystem. So here we can disable all echo writes via the echo enable register, and the echo buffer lives in memory in audio RAM and is addressed by the echo source address and echo delay registers. The output of the echo buffer then passes through the FIR filter and is multiplied with the main echo volume, and also part of the echo signal can pass back into itself, creating a feedback with the echo feedback factor, which actually allows you to repeat some snippet of audio multiple times, which actually makes this into an echo effect and not just a delay effect. So here we can see those two paths combined, from the top the echo and from the left the main volume. And now we enter the analog domain with a digital to analog converter and a small preamp, and an analog mixer now combines the synthesizer output with the cartridge analog audio in and the expansion port audio in. So cartridges could have their own sound processors on them and output their own audio, and also the expansion ports could do that. I think the Satellaview does that sometimes. Nobody's exactly sure. Somebody should research that. But after the main mixer, we get the master mute switch, which is controlled by software, and also the post amplifier then passes that signal into the various output streams like the RF generator and the RCA jacks. Yeah, so that's the entire pipeline, and now I'm going to explain the various parts that we haven't looked at in detail yet. First of all, how are BRR samples actually found and played? Well, there's a sample directory, which is a single page in memory, which contains 64 entries, 4 bytes each, and which entry to use for a voice is determined by the source number register. Yeah, So this contains, of course, the start address where we should start reading BRR blocks from when we start playing the sample, and a loop address where we should loop back to once we have finished playing and we read a loop flag at the very final block. Now the loop address doesn't have to be within the sample itself. It can be in an entirely different location in memory. The BRR decoder really doesn't care. You can have multiple samples that have the same looped section of audio if you really want to. I guess you can do some interesting things there. But this actually means that the source numbers that you can read in a register viewer are pretty intuitive because they actually specify logical sample numbers and not just random addresses. Now, for envelopes, this is the way that we shape audio and determine what kind of, it's a very important part of how how a certain note will actually sound. So the DSP can do ADSR envelopes. ADSR stands for attack, decay, sustain, release, and it's still the standard modern way of modeling envelopes on modern synthesizers. Attack means how fast do we reach maximum volume once we start playing. Decay means how fast do we drop off from that maximum volume afterwards. Sustain means what volume do we want to hold effectively forever until we let go of the notes. And once we let go or stop playing, release determines how fast do we reach silence. And this mode is enabled by setting the 7th bit of the VN ADSR register 1, the lower register, to 1. And this is the way that it actually works on the DSP chip. So every attack rate step, we first of all, we have to receive a key on signal, of course. That's again 1 bit per voice in a special hardware register. And once that happens, we increment the envelope volume by 32 every attack rate step until we reach effectively maximum volume. After that, we decrement with a multiplication factor of 0.996 every decay rate step. So this gives us an exponential decrease, slowing down over time. Once we reach the user-defined sustain level, we again decrement by 0.996 every sustain rate step. And once we reach a key off signal, 1 bit per voice, we reach the release phase, which is hardware fixed to -8 every 1 step. So what are those rates and what are those steps? So the rates are controlled by a rate table. So the input rate is a symbolic 5-bit value, which determines how many samples we wait until we take the next step. And this means if you put in 0, there's never going to be a step. So we're never going to change anything. And that's how we can achieve actual infinite sustain by setting the sustain rate to 0, and then that means that the sustain step is never taken. And you can go up to 1 step every single sample, which is, for example, what the release does. So the way that this is actually stored in the register is this, and the sustain level is basically just stored with a factor of hex 100. And the gain mode is a little bit of a simpler envelope mode. You enable that by setting the 7th bit of the ADSR register to 0, and you can then either choose between a constant envelope gain by setting the 7th bit of the gain register to 0, or a gain curve, a fixed gain curve, which you can use by setting that 7th bit to 1. So fixed gain volume is pretty much self-explanatory. It's always going to stay at a certain gain, a certain volume. Now the gain curves are more interesting. Those are the 4, if you look in the register, it has 4 different modes. That's the gain curve part, bits 5 and 6. And those are the 4 modes in order, 0 to 3. The first mode is linear decrease, which decreases the volume by -38 every gain rate step. Exponential decrease, again, uses the infamous 0.996 factor. Linear increase uses the +32 step, and bend increase also uses +32 until we reach a value of 600. After that, it's going to increase by only 8, so you get a slightly lower increase in the upper volume register. And the gain rate, again, uses the gain table, which we saw before. It's the exact same behavior. So you might now wonder, what are these decrease modes? Like, if we start with a sample, the envelope is going to be at 0, and if we then enable a decrease mode, like it can't go below 0, that doesn't make any sense. That's true. That's also not the way that it's intended to be used, because this is intended to be used for very fine-grained control. So by switching between different envelope modes during actual sample playback, you can like first switch to one of the increase modes, and then switch to a fixed gain mode, and then switch to a decrease mode, or maybe again to an increase mode or whatever. There's many things you can do with that by controlling it very precisely from software, and that's really what this is intended for. So let's move on to the noise generator, global for all voices. It uses a linear feedback shift register to create a random stream of samples, which the rate of which can again be controlled by one of these rate table entries. It's in the flags register in this case, kind of weird, like a global control register which also contains the mute flag. So the way that a linear feedback shift register works is we take the lower two bits, XOR them together, shift all the bits one right, and take that XORed bit and put it into the top. This actually turns out to be a pretty good pseudo-random number generator given how easy it is to implement in hardware. And also if you put in a certain initialization value, which the hardware does, it will go through all of the possible 15-bit numbers eventually. So echo in hardware with a RAM buffer works like this. Initially, we have to consider that we have like some start address of the echo buffer and some end address. But that's not really how the hardware sees it. Effectively, after the end address, we just jump back to the start address. There's no real concept of start and end as far as the hardware is concerned. So we consider this a ring buffer, which is also used in other areas. And the entries are not really bytes, but instead two 16-bit samples, one for the left channel, one for the right channel. So every entry is 4 bytes long. And we have a certain pointer to the next echo input. So we read out that value here with negative echo delay. And that is the output of the echo buffer system. And then we write back into that exact memory location the current input value that we were given. And then we move on to the next memory address and, of course, wrap around at the end. And what that allows us to do is that by the time we wrap around to that initial value that we just wrote, that value will have been delayed by the amount of samples that fit into this buffer. And that allows us to perform these delay effects or echo effects if we write things into it multiple times. So the way that this is controlled exactly in hardware, we have the echo source address register, which controls the page where the buffer starts, and the echo delay register controls the buffer size in multiples of 512 samples or 2048 bytes. So if you really want to, you can set that to 32 kilobit almost, which will take up like half the audio RAM. I guess then you don't have any space for code or data or samples. But that allows you to have an echo time of around about 240 milliseconds, which is pretty cool. And the delay of 0 and like buffer size of 4 is just because there's an internal buffer register in the echo subsystem. So that means you can never have a true zero echo. Zero delay echo. And the other registers you should already know about. So the FIR filter is the thing that's directly after the echo buffer. So FIR stands for finite impulse response. Well, what does that mean? This is the textbook definition from my German signal processing textbook. So suffice it to say, I'm not going to explain to you why it is called FIR. But the cool thing about finite impulse response filters is that you can implement them by multiplying certain factors, here signed 8-bit coefficients, with the previous output samples of the echo buffer, and add all of those together. And this actually allows you to do repeated echo, of course, by outputting the sample again. It allows you to do low pass, high pass, various various reverb effects and other EQ effects, which is pretty incredible for just some factors. I mean, you have to know what you're doing, but it's possible. So that's pretty much all the hardware explained. The rest of my time will be spent on demoing what you can do with all of this. So let's start with something that you're hopefully all familiar with, the Super Mario World overworld theme. On the right here you can see all of the various registers just scrolling by and messing. There's some very nice labeling there. Also, if you want to look this up for yourself for your favorite game, how exactly the voices are used. For example, you can tell that some of the voices are only used for sound effects and not for the music. And for sound effects, if you pay attention to the orange here, what is that? The ports, yeah, the CPU S-SMP ports. You can see those always changing briefly just around the sound effects. And that's how most of the games actually do it. They will send small signals over the ports from the CPU to the S-SMP whenever it needs to play certain sound effects corresponding to gameplay. Okay. Then there's also people who say, well, we have this nice audio coprocessor. We don't care. We're just going to stream S-SMP samples directly from the main CPU to the DSP. And now you really have to pay attention to the ports here, all of the 4 ports, once the actual music starts. You can see it is changing in the rhythm with the music, and I actually stepped through the code. They basically just use the S-SMP to read out the register data that is coming from the main CPU and write it directly to the DSP chip, which I think is kind of pointless, but also very good because you can spend more memory on samples and less memory on playback data. Yeah, this is a theme that I have heard way too much. I just wanted to show you how some of the music looks in an oscilloscope view, because that's what we do. You can tell that channel 8 is reserved for sound effects. There's no sound effects playing here, of course. And also maybe channel 7 is a good example of how they do vibrato by changing the playback frequency very quickly with the pitch registers that we saw before. That's a fun little tune. And finally, just to demo what you can do if you actually put in a bunch of work and take up almost all of the audio RAM with just a single song and have access to modern trackers, but it actually works on hardware. This is a cover of a older arcade game, I think, yeah, from 1985, and Blue Electric covered that recently, just to give you an impression of how actually very amazing this sound chip can be. Also, no channels reserved for sound effects. Let it play out in its entirety, but unfortunately we don't have any more time, so I'm just gonna go over to the end. You can watch all of his covers on YouTube. They're pretty great, and there's many other people that I probably don't even know of who are doing amazing things with this architecture and yeah, with this sound system. So these are all of the main resources that I used in putting together this talk. And most importantly, the full SNES manual contains all of the hardware details that I couldn't even go over here, like rounding errors and various ways of how the hardware glitches out when you give it interesting inputs. Also, the SPC700 video series by IsoFreeze, Retro Game Mechanics Explained, was a huge inspiration for me and contains a lot of cool graphics. And finally, my own manual at the very bottom is, in my opinion, the best assembly manual, but I'm biased, so because I wrote it. Anyways, if you want to get involved, there is a bunch of different trackers available. I like Furnace, which is actually a really new one, only about 2 years old, but as far as I can tell, its hardware emulation is very accurate, and you can make some interesting songs with that. You might want to write your own sound engine if you're interested in some assembly programming. Also, I would really love for someone to reverse engineer those chips, because as you saw, there's very high resolution die shots available. I think you can do the whole thing that the Visual 6502 people did with these chips. So I would really love if someone could actually do that who knew what they were doing. And of course, if you want to get involved with SPC700, my little assembler for this architecture, you can try that in your browser. There's developer help available, and just talk to me. I have a bunch of things that I want to do with that. So yeah, thank you for listening.
Although unexpected, we do have some time for a short Q&A. So please line up at the microphones, and we start with the Signal Angel. Please, go ahead.
Yes, such an advanced sound chip just begs to be used for unintended things. Are you aware of any games that used the chip for non-sound related things?
That is a good question. I've asked myself that as well. No, I'm not aware. But also, to be fair, I haven't really looked deeply into many sound engines. I've mainly looked into the NBA and NBA Live 95 sound and the Super Metroid sound engine. So unfortunately, no, I can't answer that.
Thank you. Okay. Microphone number 1, and please keep in mind that it's a question, not a comment.
Yeah. So back in the day when you wanted to develop a game, did you get any tools at all from Nintendo or Sony or the other distributors of the chips?
I don't actually know. That's a good question. I haven't found anything like that. There's not that much information on the chip available beyond the resources that I showed. So I don't know.
So all the people wrote their own trackers.
They probably wrote their own trackers. I'm pretty sure. Mostly thinking about how they compressed BRR samples. Did they have like Sony software for that? I don't know, unfortunately.
Okay, thanks.
Do we have more questions from the Signal Angel? Yes.
Yes. Do you know if any official software uses BCD instructions?
I haven't found any software that uses BCD. The exchange nibbles instruction is kind of BCD support, but that's used more often in various engines. But no, I'm not aware.
Okay, microphone number 1 again, please.
Hi. The pitch modulation that you mentioned, it looks like that you can do FM modulation with it.
Yes.
Are you aware of anything that uses it for that? Maybe with even multiple operators, channels for operators?
Yeah, I was looking around, but I so far couldn't find anything. There's various things that look like they use pitch modulation, especially modern things, but always when I looked into the tracker commands, there was nothing about pitch modulation, so I'm pretty sure it's underutilized.
Okay, thanks.
Okay, I think we are coming up to the last question. Do you have one, Signal?
Last question. How did you get interested into this topic, like writing an emulator, writing games and such?
No, I was really intrigued by the video series from Retro Game Mechanics Explained, which I also showed here, mainly because I come from the audio side. I've worked with various codecs and written audio stacks and whatnot, so I was mainly interested in the audio side and not really the games or assembler side, at least initially. And then I started writing the assembler, which made me learn about the entire architecture.
Okay, thanks a lot. Huge round of applause for Kleines Filmröhrchen.